Forces are the basic underpinnings of the universe, and it's how people first began grasping the true nature of how stuff works. As a result, compared to some of the stuff you'll study later in the year, or at IB if you so choose, it's comparatively simple. Yet understanding it well means you can understand everything about how stuff works, how stuff moves, how stuff stops, and how stuff stays in motion. Force is a product of something with mass accelerating. That is, it's changing its speed. It's going forward or it's going back. If it's got mass, it's capable of producing force. If you accelerate it, if you apply this concept in reverse, it requires force to stop something from moving. That is, if it's already got a speed of 5 and you want it to slow down, you have to apply force to decelerate it. Understand that this doesn't mention speed. An object moving at a constant velocity is not experiencing any force because it isn't changing velocity, which is acceleration. Notice also that I said velocity and not speed because force is a vector. Remember that. Force has direction. This is critical in understanding force, and it's the keys to understanding gravity and the principle behind rocketry and orbits. Now, because you can't write force as a product of mass times acceleration every time you want to find the net force of an object, there's an equation derived from that observation. Pause the video for a second and try to think of it yourself before we tell you. It's F equals ma, where F is force, m is mass, and a is acceleration. These are pretty common variables, so it'd be useful to not just remember the formula, but what the variables represent, because there's a bunch of other formulae that use them. What's also key to note here is that the units of force, that is F, are kg meters per second squared. Now, based on what the constituents are, that is mass and acceleration, you can see how that comes about, right? Kg meters per second squared, because acceleration is meters per second squared and kg is mass, right? Remember when we said force is a vector? You should, because it was a few seconds ago. Because of that quality, you can have any number of different forces acting on an object in different directions, or in the same direction. What happens then? Well, if they're in the same direction, it's pretty easy. Just add the two vectors, right? Just add this to this, and that'll be your resultant force. If they're in different directions, however, that complicates things a little bit. Take this perfectly cubic cube. It's a cube, guys, trust me. Now, if it's got a force of 5 newtons acting towards the right, and a force of 5 newtons acting down, what's the resultant force? Well, one easy way to do this is to draw a head-to-tail diagram, where the length of the arrow is the magnitude of the force. That is, this, if this is 5 centimeters and you ascribe 1 centimeter to 1 newton of force, this is 5 newtons. Now, you draw that from tail to head. Now, let's go the head-to-tail method because the tail of the next vector adds on directly to the head of the previous vector. So now we know that 5 newtons down is the second vector. So we'll draw a vector down 5 centimeters from its head here. Now we have this, we've almost got a triangle. We can join these two and have a right angle triangle. Now, if you guys have been paying attention in math class, you should know that a squared plus b squared equals to c squared. So just add this to this and do the square root. That should give you the resultant force on an object. Today we looked at the basics of forces and how to add vectors using the head-to-tail method. Next time we'll cover momentum and impulse.